So far we have discussed the common source amplifier using an NMOS transistor in some detail, including a variety of schemes for biasing the transistor. Earlier in the course I said that NMOS transistor is just an example. It is the most popular device being used today, the MOS transistor, but you could use the same principles that I described to design amplifiers using other devices. What we'll do in this lesson is to look at other devices that have been there in the past and probably will come up in the future, and show that essentially you will be plotting the device characteristics and from there choosing the right operating point for the amplifier, and hopefully any device that comes up in the future you should be able to look at the characteristics and set the operating point correctly and use it as an amplifier or use it for any other function that you wish. Okay. Now, if you look back at history, in the first half of 20th century, these devices known as vacuum tubes came into being and they became quite popular, and they were the ones that were first used to amplify signals in a wide range of applications. Okay. And the first of those types of amplifier devices is what is known as a triode. Okay. And a triode had a symbol something like this. These are the three terminals corresponding to the drain, gate and source of the MOS transistor. The drain corresponds to what was known as the plate or anode, and the source corresponds to what is known as a cathode, and the gate corresponds to what is known as a grid. Okay. And in order for the vacuum tubes to function properly, you also had to have a heater. The way these things worked is by heating the cathode so that it emits electrons and they are captured by the anode, and the number of electrons being captured by the anode is controlled by the voltage on the grid. Okay. So you can see that there is a very close correspondence to the terminals of the MOS transistor. Okay. This would be the VGS and the voltage between anode and cathode would be the VDS. The only difference of course is in the absolute value of the voltages that you would apply. It turns out that the VGS, grid to cathode voltage, would always be less than 0, and what is equivalent of the drain source voltage, the anode to cathode voltage or plate to cathode voltage, would be in the hundreds of volts. Okay. Now, just like the MOS transistor, the grid current was very small, and you can see here what is shown here are the characteristics. What is shown here are the characteristics, specifically they are ID versus VDS. Okay, I have labeled them I out versus V out, basically the output characteristics of the triode, and you can think of it as ID versus VDS characteristics for different values of grid voltage or different values of VGS. You can see it's 0 volts, -1, -2 and so on. So just like in a MOS transistor, as VGS increases, when I say increases, here it is becoming less and less negative, the current will increase. Okay. Now the one key difference between a MOS transistor and this, the characteristics are basically these curves given here. The key difference that you see is in a MOS transistor, beyond a certain value of VDS, the characteristics become flat, and that's the preferred region of operation for an amplifier. Whereas in this case you don't see a flat region at all. Okay, the current is going on increasing, and in fact it looks more like the characteristics in this region of the MOS transistor. Okay, they look like the characteristics in this region of the MOS transistor near the origin. The slope is not negligible, the slope is quite high, and in fact this region is called the triode region because the characteristics in this region resembles the characteristics of a triode. Okay, so this is not an ideal amplifier, it doesn't have all the desired characteristics, but you could still make amplifiers. Okay, and it was being used. Now later people got ideas about how to make the device better. what they did was, so we have the three terminals of the triode, plate, grid and cathode, and for a variety of technical reasons which I won't discuss here, they found that they could add another terminal and make it better, and this terminal had to be biased such that its voltage is positive, the same as the drain or even higher, and that device is known as a tetrode, meaning it has 4 electrodes, and somebody else found that it will be even better if you add a fifth one here, and this is biased with a negative voltage. Okay, it's connected to ground in most circuits, and such a device is known as a pentode. Okay, and here I show the I out versus V out, basically ID versus VDS characteristics of a pentode. As with the triode, the grid or the gate voltage is negative. I hope you can see here the gate voltage here is 0, and here it's -4, -6 and so on. So as the gate voltage becomes more positive, the current increases, and also you can see that this part of the characteristics, it resembles the MOSFET. There is a flat region, which means that a pentode is a much better amplifier device than a triode. Remember, before we did anything, we tried to look at what the characteristics of an amplifier should be, and we found that Y22 should be very small, close to 0, and you can clearly see that Y22 of a pentode approximates that, whereas that for a triode did not do it at all. Okay, so what is the difference between a MOS transistor and a pentode? Typically today when you talk about MOS transistors, there is of course a huge variety, but for most amplifier devices, the x-axis VDS will be a few volts at most, whereas here you can see that it's going all the way to 500 volts. Okay, but the principles are exactly the same. You choose some operating point here and bias your amplifier there so that you get a pretty high gain. Of course, you have to be a little more careful with building these circuits, because instead of 5 volts you have 500 volts, and you can't be sticking your finger everywhere in the circuit and getting an electric shock and so on. Okay, but the pentode is rather close to a MOS transistor, and this was a very popular amplifier device. Okay, now here I show the simulated ID versus VDS characteristics of a real MOS transistor that I have used in many designs, and you can see that it sort of follows what we have been using. It won't be exactly square law. Okay, so like everything else, there will be approximate models which help us carry out any calculations at all, and there will be more detailed models which will show you all kinds of deviations from the approximate model. The approximate model is square law. This won't be exactly square law, but you can see qualitatively the resemblance, the triode region, the saturation region, and the increase in current with VGS. It's not labeled here, but you can see that VGS has been varied from 0 to 1.5 volts in some small steps. Okay, now here we have another device which is known as an NPN transistor, which we will discuss later in the course. This was the type of semiconductor transistor that came after the vacuum tubes. It displaced the vacuum tubes, and it was itself kind of displaced by the MOS transistor for many applications. These are still being used, but the MOS is more popular. Okay, so this has 3 terminals, collector, base and emitter, which correspond to respectively the drain, gate and the source. And you can see the characteristics are similar. There is a part of the characteristic where this I out versus V out is very flat, meaning the amplifier must be biased in this region. You can also see that the region corresponding to the triode region is very small. Okay, in a MOS transistor the triode region is quite useful. It turns out that in a bipolar junction transistor such as this, it's not useful at all. Okay, and this shows a commercially available MOS transistor and its characteristics. Okay, this is ID versus VDS, and you can see it sort of follows the characteristics that we have described. It does not quite square law, because for equal increments in gate voltage, the increments in drain current are not increasing sharply, but it does follow it qualitatively. And this shows I out versus V in, meaning ID versus VGS for the same type of transistor, and you can see that it follows this square law characteristic. And what's also shown here are characteristics at different temperatures. Earlier I had mentioned that the characteristics of all these change with temperature, and you can see that here. You can see that both the threshold voltage and the current factor are changing with temperature. Okay. Now let's go to some futuristic devices that people have been working on. These are still in the lab stage. You cannot buy an integrated circuit which use these transistors, but people have been trying to use all kinds of other materials to make transistors in the hope that some of them will be even better than the transistors that we already have. Okay, so this is some transistor. I'll continue to use the MOS symbol for it, and again what I've shown are the ID versus VDS characteristics. You may have heard of this material called graphene. It appears in the news for all kinds of reasons, and here people have tried to make a transistor using graphene, and you can see that there are some parts of the characteristics where it becomes flat, like this red curve here, and these brown ones are not quite becoming flat. So obviously the aim of the people designing devices is to get these flat regions so that you can make good amplifiers. Okay, but even if you don't have this flat region, you can use it as an amplifier. It will be a poorer amplifier, you will get lower gain, but just like the triode, you could possibly use that. Okay, and you can see that the current and voltage are similar to what you would get in a MOS transistor. And this is a picture which I picked from the web. I mean, you go to Google and search for organic transistors. Don't worry about all the details. There are some many curves here, but you can see that it has characteristics like these. You can see it starts from 0, goes up, and then kind of becomes flat, and here it goes up in a strange way, but it becomes flat again. So essentially any transistor that you make must have this type of characteristic. That's what people are aiming for, and if you want to use it as an amplifier, obviously you must bias it in the flat region like here. Okay, and here is another variety of transistors known as TFT transistors. Again, this is obtained from a web search. You can see it has these regions where there is substantial variation of I with VDS, and these regions where the curves become flat. By the way, everywhere what I am showing are the ID versus VDS characteristics, and you can realize that these are crucial ones. If you have flat regions in that, you can make very good amplifiers. Okay, you need to look at both parts of the characteristics, ID versus VGS and ID versus VDS, and ID versus VGS must have a very high slope, and ID versus VDS must be as flat as possible. Okay, and just for fun, I am showing you an example of a vacuum tube amplifier. It uses a pentode. So now I don't want to confuse you too much, so just ignore this and that electrode. Like I mentioned earlier, this one is simply connected to the supply voltage and this one is connected to ground. Okay, if you exclude those two, the remaining 3 terminals correspond to the drain, gate and source of a MOS transistor. Okay, and this is taken from some circuit from EDN, and it says that the quiescent current is 5 milliamps. Okay, so essentially it means that at the operating point 5 milliamps is flowing here into the drain or into the plate, and it's coming out of the source or the cathode. So this I'll approximate to 500 ohms and say that the source is at 2.5 volts if 5 milliamps is going through 500 ohms. Okay, and hopefully you will be able to recognize the structure. Okay, this is one of the circuits that we discussed. This is the circuit where you of course have the drain bias resistor, which corresponds to this, and you would like to bias with a current source at the source terminal, but because current sources are harder to implement, you substitute a resistor instead. That's exactly what this is. Okay, so this is essentially what we have here is a common source amplifier with a resistance in the source, which is standing in for a current source at the source of the transistor. Okay, so this is source feedback bias, and that's exactly what is used here. And you can see that there is a big capacitor from the source terminal to ground or the cathode to ground. Okay, so if you remember, this is exactly what we did for our common source amplifier as well. And the reason I'm going through this amplifier is it's not likely that you will see this particular amplifier now. This is quite obsolete, except some audio enthusiasts still use them. But if you do encounter a circuit like this, or maybe from a futuristic device, you shouldn't get confused. Or if you are given a futuristic device, you should be able to use the same principles to design the amplifier. Okay. And you can also see the output side. This is quite familiar. We have AC coupling to take the output. This is C2, and in this case it is some 1 nanofarad device. And also, when we bias it like this, we would in case of a MOSFET, bias the gate using a voltage divider. Here you can see this is relevant, this capacitor is relevant only for signals. So in the quiescent condition, the gate of the vacuum tube or the grid of the vacuum tube is connected to 0. Now remember, it is connected to 0, but the source or the cathode is at 2.5 volts. So this is operating with a quiescent VGS of minus 2.5 volts. And that's correct. In case of a MOS transistor, the type that I described, you needed a positive gate source voltage, whereas in case of a vacuum tube, in this case, you need a negative gate source voltage. So it's simply connected to ground. You don't see a voltage divider connected to the grid terminal. You see just a resistor connected to ground. Okay. And you couple the signal using a capacitor C1. Now there is another additional detail here. This resistor is made variable. This is, I guess, for an audio application, and this variable resistor acts as a volume control as well, or a gain control as well. Okay. And of course the supply voltage is much higher than what we are used to. It is 120 volts. Okay. So essentially this is nothing but a common source amplifier with source feedback bias, and the current source at the source terminal replaced by a resistor. Okay. So the only difference between this and the MOS amplifier are the operating point. Okay. You need a negative VGS and VDS in the many tens of volts for a vacuum tube, whereas in our circuits we have a couple of volts of VGS and a few more volts of VDS. Okay. So this is a lesson of the more general type, just to expose you to more things, and you can in fact go to the internet and look for amplifiers using other devices. Even if we have not discussed that particular device in the class, you should still be able to understand the amplifier topologies as long as they correspond to the common source amplifier. Okay. So as we go along, we will also discuss other types of amplifiers. Okay.